July 17, 1981, hundreds gathered for a dance in Kansas City. No warning. Suddenly, the walkways above gave way. 114 people were killed, and more than twice that number were injured. The calculations had checked out. The drawing changes looked minor. Yet a single connection failed catastrophically because good enough math hid how forces truly moved through the structure. If every load was accounted for, how could one small shift end in disaster? Steel rods, stretching from the ceiling to the floor, defined the heart of the Hyatt Regency's atrium. The original design called for each hanger rod to run in one continuous line, threading through the fourth-floor walkway, then passing straight down through the second-floor walkway, before anchoring at the ceiling above. At each level, the rods simply continued on, never stopping, never splitting. This geometry meant that the load from the upper walkway traveled directly through the rod, bypassing the lower walkway's supporting beam almost entirely. The forces from people standing on the fourth-floor bridge moved down the rod, through the air, and into the ceiling truss, leaving the second-floor walkway's beam to carry only its own weight plus the people standing on it. In this arrangement, each node, the place where rod and beam met, had a clear independent job. The upper rod segment carried the fourth-floor walkway's load up to the ceiling. The lower rod segment continued through supporting the second-floor walkway below. The two walkways did not share their weight at any single connection. If one beam or rod segment failed, the others could still carry their own loads. This separation of force paths preserved redundancy. No single connection had to bear the combined weight of both walkways. The original shop drawings showed this clearly. A continuous rod passed through holes in the top and bottom flanges of both walkways' box beams. Arrows on the diagrams traced the path of the load from the floor below up through the rod and out to the ceiling. Each walkway's weight followed its own route, with no doubling at any node. This topology, simple, direct, and independent, defined the system's baseline safety. Engineering teams prepared calculation sheets for each walkway member. They checked tension in the steel rods, bending in the box beams, and the overall strength of the welded joints. The numbers aligned with the American Institute of Steel Construction Code in effect during the late 1970s. Each rod was sized to withstand expected tension forces. The beams passed checks for bending under their own weight and the weight of a full crowd. Welds along the seams of the box beams were measured against code requirements, and safety margins were tabulated for each connection. At every step, the calculations focused on individual components, treating each as a separate element. Code formulas provided clear boundaries: how much force a rod could take before yielding, how much shear a weld could resist before tearing, how much bending a box beam could safely carry. But these checks stopped at the component level. The system as a whole, the way forces traveled from the walkway through the rods and beams and up to the ceiling, was not recalculated once the drawings were approved. The concept of reserve capacity appeared in the notes, the difference between what a connection could carry and what it was expected to see. Yet no one quantified how much reserve actually remained at each node. As long as the numbers for rods and beams looked acceptable on paper, the design was considered safe. This approach left a gap. The calculations never examined whether the connections could handle unexpected combinations of force or how a change in one detail might affect the entire load path. The assurance of safety rested on the sum of individual checks, not on a full understanding of how the system would behave if the details changed. Shop drawings from Haven Steel arrived with a subtle but decisive change. Instead of a single hanger rod running through both walkways, the new detail split the rod into two segments joined by a nut and washer at the fourth-floor box beam. On paper, the geometry looked similar. In practice, it altered the way forces moved through the structure. The upper rod now ended at the fourth-floor beam, bearing down on the top flange. The lower rod began at the underside, carrying the second-floor walkway below. To understand what changed, imagine the forces as simple numbers. Suppose each walkway, fully loaded, contributed 50 kilonewtons to its connection. In the original design, the fourth-floor beam only saw the load from its own walkway, 50 kilonewtons, because the rod continued through, and the upper walkway's weight passed directly to the ceiling. The lower beam carried its own 50 kilonewtons, isolated from the upper's burden. With the split rod detail, the fourth-floor box beam faced a new reality. The upper rod pressed down with 50 kilonewtons from the fourth-floor walkway. The lower rod attached at the same point, and it pulled down with another 50 kilonewtons from the second-floor walkway. The forces combined at the node, 50 plus 50, for a total of 100 kilonewtons. The box beam web, never designed for this sum, now had to carry twice the load it was meant to resist. The free body diagram for the connection became simple. The sum of vertical forces equals the upper walkway load plus the lower walkway load. The arithmetic proved the system's new weakness. What looked like a minor fabrication convenience had, in a single step, doubled the demand on a single piece of steel. Investigators from the National Bureau of Standards arrived in Kansas City with a clear mandate: determine exactly how and why the walkway connections failed. Their approach combined laboratory testing, detailed analysis of the debris, and a close reading of the shop drawings. In the lab, full-size fourth-floor box beam specimens were assembled to replicate the revised hanger rod detail. Incremental loads were applied, carefully measuring at what point the steel would yield or rupture. The results were unambiguous. Every test specimen failed at the same location, the web of the fourth-floor box beam, directly where the upper and lower rods converged. The web tore open along the welded seam, unable to resist the combined vertical force. Calculations confirmed what the physical evidence showed. The actual load at these nodes reached approximately 180,000 pounds, nearly double the web's tested capacity, which topped out at around 90,000 pounds before failure. The welds, though compliant with code dimensions, could not hold against this magnitude of shear. Metallurgical inspection of the failed beams from the collapse site showed identical fracture patterns to those produced in the laboratory. The sequence was clear. As the crowd filled the walkway, the stress at the east end of the middle box beam surpassed the steel's limit. The weld cracked, the web split, and the connection unraveled in seconds. The National Bureau of Standards team's forensic work linked the arithmetic overload directly to the physical rupture. No hidden flaw, no missing bolt, just a connection asked to carry more than it could ever withstand. The numbers matched the scars left in steel. This was not a failure of calculation, but a failure to recognize what the math truly meant for the material. Reserve capacity is the buffer between what a structure can carry and the maximum load it is expected to see. In a well-designed system, this margin absorbs unexpected stresses and minor errors, providing time for warning signs to appear before failure. The original walkway connections held a comfortable reserve. Capacity charts from the period show that nodes could withstand well over their design loads. But after the rod detail changed, the margin at the critical fourth-floor node dropped to almost zero. The combined forces at this single point meant that any overload, even a modest crowd or a small construction flaw, could push the connection past its limit. Hierarchy in structural design means that primary elements like the rods should fail only after secondary ones, preserving the system's integrity. The revised detail inverted this order. The box beam web, never intended as the main load path, became the weakest link. The system now depended on a single connection with no backup if it gave way. Professional responsibility in structural engineering extends beyond checking calculations for individual parts. When the hanger rod detail changed, the increase in load at the fourth-floor connection exceeded the 10% threshold that should have triggered a full system review. Yet no reanalysis was performed. The engineer of record approved the revised shop drawings, the fabricator implemented the new detail, and the building department relied on the stamped documents. Each party assumed the change was minor, and that the numbers still worked. But the workflow broke down where it mattered most, in verifying how forces would actually move through the altered structure. The duty to question, to recalculate, and to ensure safety at the system level was shared, yet it was missed by all. Today, every building code and engineering classroom remembers this lesson. Calculations alone do not guarantee safety. When a single overlooked detail can bring down an entire structure, vigilance becomes the true foundation. In engineering, there is no substitute for understanding how forces really move. The margin for error is gone.